Hello dear all, welcome to Pen and Paper Chemistry on YouTube. We are going to continue with our topic of phenols and we are talking about properties over here. We have already covered the preparation and some of the basic characteristics of phenols in our earlier videos. Please make sure that you have the pen and paper ready so that we can together practice writing the chemical equations and gain confidence in the topic. Just by watching this video alone, I don't think so we'd be able to do the justice to the topic required for learning this fully. In this video, we shall be talking about the properties of phenols, and as you may recall, we had drawn a bigger flow chart depicting all the different properties of phenol. We are taking one aspect of those properties and we are going to talk about the reactions involving the breaking of the OH bond. So we know that phenol has OH group. Here we are going to talk about how and when this OH bond prefers to break. Under this heading, we have three sets of properties: acidic nature, we shall be talking about acylation, and we shall be talking about benzoylation. All these reactions will become very, very easy and very simple to understand if you keep writing with me as we go ahead. And to make things easy for you, you can either take a screenshot of this chart or you can draw it yourself and keep it handy as we go ahead with the first set of equations. So we have got the chart saying that phenols are acidic in nature. Now what is the property of an acid? An acid reacts with an active metal like sodium, potassium, magnesium, you even have aluminium to liberate hydrogen gas. Acids react with bases to form salt and water. Acids turn blue litmus to red, and acids react with carbonates and bicarbonates to give us carbon dioxide, right? Now let us see that out of these properties, what all properties are shown by phenols to us. Yes, phenols do react with active metals to liberate hydrogen. Phenols do turn blue litmus to red. Phenols do react with alkalis to form salt and water. Oh, but look at that. They do not react with carbonates and bicarbonates to liberate carbon dioxide. So meaning to say, phenols cannot push out the C double bond O group from a carbonate or a bicarbonate. In other words, they are less acidic than the carbonic acid, and they are even less acidic than carboxylic acids. The details of this aspect we will do further. One very interesting point, if you remember the topic of Grignard's reagent, we had said that any compound with an active hydrogen, that is an acidic hydrogen, will be able to react with Grignard's reagent to give us an alkane. So these are the properties that we are going to write together now. Would you like to try writing these reactions on your own? So what do you have to do? You take phenol C6H5OH, react it with sodium. So we are talking about the breaking of the OH bond, right? So break this bond, H gets replaced by Na, C6H5ONa plus hydrogen H. Now we know that hydrogen does not exist as an atom, so we're going to write it as a molecule. In other words, I need to balance this equation, so we have 2 and a 2 and a 2. Many a times in your textbooks, you would have seen the reaction written like this. C6H5OH plus Na gives you C6H5ONa plus half hydrogen. Now this half is only to indicate that for one molecule of phenol, one atom of hydrogen is liberated. Both the equations mean the same thing. There is nothing wrong with either of them. So either you put half hydrogen and you keep these as 1, 1, 1, or you take one molecule of hydrogen and the rest of the equation takes a coefficient 2. Now let us write the name of this. This is called sodium phenooxide. Now phenooxide is something similar to alkoxide. Can you recall what we did in the previous video? From alcohols, when hydrogen is removed, you get the alkoxide ion, right? Similarly, from phenol, when you remove the hydrogen, you will get the phenooxide ion, C6H5, right? Not H6, C6H5. O negative plus H positive. This is phenooxide ion, PHENOXIDE, and sodium is the positive entity over here. So we have sodium phenooxide. Have you written the reaction? Okay, next. Now, phenol reacts with bases. So C6H5OH plus NaOH. What will you get? Again, salt and water. Positive, negative, negative, positive. So C6H5ONA. What will be the name of this compound? Very good. This is again sodium phenooxide. So you're getting salt and water. So this also goes on to show the acidic property of phenol. Third, phenols react with, or actually they convert blue litmus to red. That is why if you notice in the flow chart, I have written blue litmus in blue and red in red, just for easy recall so that we are able to connect to this. Now let's go back to our learning that we did in alcohols. Did alcohols show this reaction? Yes, they did. They liberated hydrogen on reacting with active metals. Did alcohols show this reaction? No, they didn't, right? Meaning to say that alcohols are less or more acidic than phenols. Tell me. So alcohols plus NaOH. There's no reaction. That means alcohols are less acidic compared to phenols. Right? Now, the fourth point. Phenols, C6H5OH plus carbonates or bicarbonates. So let's suppose I'm taking Na2CO3. You can write a similar, okay, let me not confuse you here, Na2CO3. Go ahead and write the reaction, positive, negative, negative, positive. So what do we get over here? C6H5ONA plus H2O plus CO2, right? This is what we should get. Sadly, this reaction does not take place. What does this mean? See, if it is an acid, it should react with carbonate and bicarbonate to give us carbon dioxide. But because this reaction is not taking place, that means phenol is not strong enough to replace the carbonate ion or cause the liberation of carbon dioxide from its compound. In other words, my phenol is less acidic compared to carbonic acid. Right? Now let us understand this difference in behavior as to why it is so that our phenols are more acidic than alcohols. When an alcohol loses a proton, C2H5OH, I'm taking the example over here, C2H5O negative plus H positive. First of all, these type of species which are proton donors are known as Bronsted acids. Similarly, if you deal with in terms of electron concept, then electron acceptors are Lewis acids and electron donors are Lewis bases. A for acceptor, A for acid. So acceptors are Lewis acid and electron donors are Lewis bases. According to the Bronsted concept, proton donors are Bronsted acids, whereas proton acceptors will be good. Okay. Have you written all this down? This will add to your knowledge at the same time. Okay. Now, our alcohol is losing a proton, forming an alkoxide ion. Similarly, our phenol also has a tendency to lose an H, forming, what do we call it as? What did we name it as a little while ago? Yes, the phenoxide ion. Now, what do you have to do for me? You have to draw the canonical structures. Again, because phenol is losing a proton or a proton donor, that means phenol is also acting as a Bronsted acid. What is left behind is the phenoxide ion, and we have done in the earlier videos that phenoxide ion is stabilized by resonance. So what are you required to do? Yes, you are supposed to draw. Please draw the canonical structures of phenoxide ion. I'm waiting for you to draw. And if you do not know, please go through the previous videos loaded under the playlist Phenol to clear your concept on resonance and canonical structures. Are you drawing? Good. If you've drawn for phenoxide ion, can you draw canonical structures for phenol as well? Go ahead, try it. Drawn the structure of phenoxide ion. Now you see over here, the ion which has been formed by loss of a proton in phenol is getting stabilized by resonance. The electron is dancing all over the place, so the game of passing the parcel is on in full swing. With a result, it becomes more stable. It is not localized as in the case of ether oxide ion. Here, the negative charge is remaining limited to oxygen. Whereas here, the electrons are dancing. We use the word delocalized. The electrons are getting delocalized over the entire hexagonal ring, the benzene ring. And this provides it more stability. So the load, only one atom is not bearing the load. The whole family is sharing the responsibility. So this explains why our phenols are more acidic than alcohols. Right? Now, a question may arise that why phenols would lose a proton in the first place when they themselves can undergo resonance. Do you remember we drew the resonating structures for phenol? Why don't you try drawing them now? Go ahead, give it a try. If you see over here now, in the case of phenol, yes, there is a sharing of electrons with the benzene ring, but in the entire process, first of all, oxygen is getting a positive charge. What type of an atom is oxygen? Electronegative or electropositive? Yes, it's a highly electronegative element. So is it happy having a positive charge onto itself? No, not as much, right? Also, if you notice in this game of passing the parcel, the negative is moving away from the positive at each step. It's gone further away over here. With the result, what will happen is there is greater charge separation in the case of phenol. Because of this greater charge separation, the positive is not happy. First, it is being put on oxygen, and secondly, we are keeping it away from the negative charge, compared to the first scenario where the negative charge is on the benzene ring, or even oxygen had a negative charge. This situation is not as much acceptable, so it does not contribute to resonance as much as a phenoxide ion would. So alcohols, yes, they are acidic, but they are weakly acidic. They do have a tendency to lose a proton when there is a proton acceptor over here. So for example, if let's say we take water or we took a base, so these are all proton acceptors. In our further videos, we shall also be comparing the acidic character of phenols with carboxylic acids, as to why this difference, what is the difference, and why carboxylic acids are more acidic than phenols. And we've already discussed why phenols are more acidic than alcohols. Coming back to our acidic nature of phenols, there's one more reaction left. Remember, phenols, because of their acidic hydrogen, will be able to react with Grignard's reagent to give us alkanes. So let us write down the reaction for the same. Again, revising what we had done earlier, alkyl magnesium halide, that is our Grignard's reagent. By the way, there is a separate set of videos on Grignard's reagent, their preparation, their usability. Don't miss out that video. It will be really, really helpful. I'm very confident. But I repeat, if you want to make your learning on organic chemistry good, if you really want to understand organic chemistry, pen and paper is the solution. That's the only way that you can understand and learn organic chemistry. There's no other way. No other way. There can be other supportive ways, but other than you writing, there's no other way that you can do organic chemistry. But if you know of some other way, please do share it in the comment section. It will be a blessing for all the other learners as well. Now, when you do alkyl magnesium halide, remember what did we do? Yes, a positive and a negative. And in the case of compounds with active hydrogen, positive and negative. So positive goes to negative and negative goes to positive. RH plus the phenoxide derivative of magnesium halide, right? Okay. Now, supposing I want to prepare methane by this reaction, what will I take? What will be R over here? So, methane means CH3H. This is what I want. So, what should be my R? Well done. It will be CH3Mg. Let's say it is Br. Now, complete the reaction with phenol. I want to prepare ethane by this method, C2H6. What is my R going to be? Well done. It is going to be C2H5MgBr. When I ask you questions during a video, please try and pause the video, think about the answer, and you will feel better connected to the channel and to the learning. Do this for yourself, not for me, not for your teachers, not for your parents. Do it for yourself and you will find that the end of the video, you'll be grinning from end to end, you'll be smiling, and you'll really enjoy your learning. We are not yet done with the properties of phenol. Oh, we've got a lot to do, esterification, benzoylation. So let me take that up in the next video, otherwise this will get too long. Let's take a little water break and come back.